Hi everyone, so today we will cover support vector machines. It is called out of the box classifier because they work well in many practical situations without needed heavy fine tuning. So this classifier is totally different what we've been learning till now. It's different from linear regression, logistic regression, trees. So we have three support vectors machines. One is called Maximum Margin Classifier and Support Vector Classifier and Support Vector Machines. The first one is conditioned with the one to work in one conditions. The data is supposed to be separable data. The second one, non-separable data, is used for, and the third one is used for nonlinear classified boundary. So Maximum Margin Classifier work when data is perfectly separable, not overlaps between classes. So we have to find the best separable line or hyperline that maximize the margin, the distance between the boundary and the closest data point. First, we need to define the hyperplane. The hyperplane, for example, if we have one-dimensional space, only one input data, one independent variables. So the hyperplane, this one, the point in the yellow one, will be separated into two parts, into two classes. But if we have two-dimensional space, that means we have x1 and x2. So our hyperplane, he will divided these our 2D dimensional space into two classes. And if we have a three-dimensional space, so will be this is 2D dimensional 2D hyperplane. It will divide our 3D dimensional space. So for example, if we have two predictors, so that means we have 2D space. In 2D space, and we have the category, we need to check if it's pass or failed. So the maximum margin classifier work, the data is supposed to be well separable, and then we should define the hyperplane that divided the classes into two classes. This is one for pass and this is one for failed. So since we have 2D predictors x1 and x2, so that means we're dealing with the 2D predicted variables, and we want to find the 1D because there's only one line, to find the 1D hyperplane which separate our data into two classes. Okay, so we have infinite hyperplanes. We have many hyperplanes. How we decide which hyperplane, the best hyperplane that separate our data? We can have many hyperplane, but we need to find the best one that separate our data. So in maximum margin classifier, from this, for example, first let's get the summary. So we have this hyperplane. It's also called our decision boundary. And we have these points. It's also called the support vectors. So the first support vectors that close to our hyperplane is called the margin. So the first support vector, it will define the margin. And so we need firstly for a candidate hyperplane, we calculate the perpendicular distance from all point to the line. So in this maximum margin classifier, firstly we have to find the perpendicular distance, for example from the hyperplane into the first point, second point, third point, we define the distance. And then the smallest distance, closest point to the line, define the margin. Which one is the closest point to the margin? Closest point to our decision boundary, it will define the margin. The first point will define the margin from both sides. So we have this line is called the margin, this line is called the margin. And the support vectors, as we say, this is the point, is called the support. The first one that will define the margin is called support vectors from both sides. And then the algorithm then choose the hyperplane that maximize this margin. So the model we choose the hyperplane that make this area is very wide because we need to set the hyperplane that is far away from our points, so it will be best separate. We don't need our line to be in here because it will be risky to classify our data. We need it in the middle. That's how maximum classifier work, margin classifier work. We have limitations in here. The first limitation, maximum margin classifier cannot be used if the two classes are not separated by a hyperplane. So we should have the hyperplane. If you don't have hyperplanes, it's not working. And the second one is very sensitive to support vector. If you see, this is the decision boundary, but if you have a support vectors, the points in here, if you have a point it is beyond the decision boundary, so the hyperplane will be changed, so very sensitive to the change in the support vectors. And we have the support vector classifier, the second method. This work with non-separable data. So in this method is also called a soft margin classifier. We will allow some observation to be incorrectly classified or to be wrong side of the margin. So if you see, we have this is 11. This is supposed to be classifier in the class number 2, the red one, and we have this is the blue one is a class number 1. So this supposed to be is classify the red one as in this classify number 2, but this is 12 number, it is give him the classes as blue, and that the model is predicted this one to be blue. And if you can see, we have also the 1 point, so this one is supposed to be belong to the blue. Okay, this one's supposed to be belong to the blue after the decision boundary, but it's classified in the wrong direction. So in this method we allow misclassification. So how this is work, we create a misclassification budget, it's called P, and this is B equal to is how much total error we are willing to allow. How much the total error? We know where there is misclassification, but we allow this misclassification. We determine that with the B, and then this P is the distance between how far a point is from its correct margin. So how far this one is to belong to this margin, so how far this is point from this margin. This is the error. So we count all the error we need to allow, and we assign that to the B value. And then the sum of these slacks, these variables x1, x2, x3 is called a slack. So the sum of these slacks is supposed to be less than or equal to B value. So we try to maximize margins, we make them wider while trying to stay within the budget. We don't need to our variables to be bigger than the total errors. So when we run our model in the R package, we will use the C, it's called cost multiplier for the error term, which is inversible related to B value. This is the total errors. And also we have limitation. Before the limitation, when the C is small, that means we have margins will be wide, but when the C is large, that means the margins will be narrow and there will be a fewer support vectors. So we try to find optimal value of C at which we get the best test performance. And the limitation, this is support vector classification is a linear classifier. It cannot classify non-linear separable data. If you have non-linear separable data, that means this one is not perfect for your model. And we have the third one is called support vector machines with kernels. This one handle non-linear boundaries. So use the kernel trick like polynomial, RBD, RBF, and sigmoid kernel to transfer input data into a higher dimensional space where it become a linear separable. So if you have non-linear boundaries, so we have three methods: polynomial and RBF and sigmoid kernel, to turn the data into non-linear boundaries. So if two classes are shaped like concentrated circles, a linear classifier won't work. So we use the non-linear boundaries. The first one is called linear kernel. This linear take inner products of two observation. So we should have two observation, and we take the inner products, and this kernel effect is support vector classifier. So this one is for linear. For linear kernel, is supposed to assume that the data is linearly separable, is equivalent to the CMV actually. And this one is used under this condition. We have high dimensional data set. Example, this is text classification. When you believe data can be separated with a straight line, you can use it when you believe the data can be straight line. So the second one is polynomial kernel. So use it power functions to create nonlinear boundaries. So if you need to create nonlinear boundaries depend on your data, so we use the polynomial kernel, and is when use data isn't linear separable but not a complex as required in RBF kernel. You want to control complexity by degree d. So the degree d, it will control the complexity of your model. And the last one we have is radial basic function. So this one is used the Gaussian. Radial kernel uses radial functions. So we use the radial functions to classify our data. And in here we have the gamma is define how much influence a single training example has. So if you have a decision if you have higher gamma, that means decision boundary is tight around support vector. But if we have a low gamma, that means you have the boundaries is smoother and more general. So this is used when the decision boundaries is very complex and nonlinear. Often this is the default in many SVM applications. So if you have decision boundary is very complex, so you can use the RBF in this model. So this is all you need. This is the theoretical part for our model. In the next video we will start implement all these methods in the R studio. So thank you for your watching, and see you in the next video.